So differential equations. This is where we get to have some fun with calculus. So a lot of the rules for physics, biology, social science end up being mathematical relations where quantities are changing. So in other words, it involves derivatives. Here's some examples of ones. You might not have seen them written this way, but you should recognise. There we go. M times the second derivative is equal to some function of x, which I've called capital F. That is, of course, Newton's second law of motion, which probably you're more used to seeing as F equals m times a. But that essentially is it. That's the differential equation for the second law of motion. This one here, you might not recognise this one. But that's the formula that controls the oscillation of something like a shock absorber or something like that. So m times the second derivative plus b times the first derivative plus some constant times x equals 0. That one there has a real fancy name. The Lotka-Volterra equation, also known as the predator-prey equation. So how populations. So it's a lot more sophisticated growth and decay equation. All these sorts of things are simply called differential equations, equations that involve derivatives. Now, the order of the differential equation, you look for the highest order of the derivative. So that very first one there would be a second order differential equation, as would the second one. The third one is just a first order differential equation. So solving them, basically, at a very simplistic level, you've been doing this. It's integration. We've been looking at very simple differential equations at this stage. You know, y dx equals x, for instance. I mean, it is a differential equation. So we have a general solution to differential equations. So that's a family of curves. That's like what we've been finding as an indefinite integral, where we go plus a constant, and the constant could be anything. So you get a family of curves as the answer. And then we have particular solutions. And that would be like our definite integral, where we've got some known numbers we can substitute in, work out what that constant is. It solves what we call an initial value problem. So some initial conditions that we know that we can solve into the problem and get the specific answer that we're looking for. So let's have a look at a more interesting one. X to y dx plus y is equal to 0. Okay, well, basically I want to get anything that has y on one side of the equation, anything that has x on the other side of the equation, and then integrate both sides with respect to the variable that we have there. So I can rearrange that equation. So you're sort of treating dy as if it's a pronumeral and dx as if it's a pronumeral, I guess. I end up with this. So we have minus the log of the absolute value of y equals the log of the absolute value of x plus some constant. Now I can use my log laws to group the x and the y together there. So I have the log of the absolute value of xy is equal to a negative constant, which means the absolute value of xy is e to the power of minus k, but if k is a constant, then e to the power of minus k is also a constant. So rather than have that exponential there, I'll just say equals a constant, and then I can just say, well, y equals some constant divided by x. Now you might be thinking, well, hey, whoa, where did the absolute value signs go? Well, I don't have to worry about it because that constant could be positive, could be negative. So it really doesn't matter about the absolute value signs in this. There is the general solution, or a picture of it. Well, it's our hyperbola that we're used to seeing, but obviously depending on what that constant is, it's placed in different spots. Now, if my initial value problem was this, so it's a way of just saying when x is equal to 1, y is equal to 1, then the constant is 1, and so that black one there is the particular solution to this problem. Our basic hyperbola, y equals 1 on x. Now we're interested in looking at linear differential equations. And that's what linear means when we're talking about differential equations. So we're not talking about y equals mx plus b. We have a function of x times y, then dy dx, then the second derivative, third derivative, fourth derivative, fifth derivative, and we keep going and we keep going. But the very last one, you'll notice, is not multiplied by some function of x. It doesn't need to be, because on the right hand side we have equals function x, so we could always divide by that coefficient of the highest derivative. It just creates a different function on the right hand side and different functions for all the coefficients of the other one. Now don't panic, we're pretty much restricted in our course to doing first order ones, so we won't be going up to those really high ones. So first order linear differential equations, something in this form. So we'll end up with the derivative plus some function of x times y is equal to some function of x. That's the situation we're interested in. Now, if function x is equal to 0, then it's just simply what we're used to doing. Because if it's equal to 0, I could move it to the other side and we work out our indefinite integral. Now, if function x does not equal 0, here's the tricky bit. We multiply everything by what we call an integrating factor. And how do we work out the integrating factor? It'll be e to the power of the integral of gx, so whatever the function is times y, dx. That's our integrating factor. So let's try one. The derivative plus 4y on x is equal to 3x squared. So I've got to work out what is my integrating factor. Well, it'll be e to the power of the integral. So let's work out that integral. The function in front of y is 4 on x. If I integrate that, I get 4 log x. So my integrating factor would be e to the power of log x to the power of 4. They cancel. Okay, I'm going to multiply everything by x to the power of 4. There's my new equation. Now, why do we do this? If you look closely at the left-hand side, what you have just done is created the answer to the product rule. Write down the first, diff the second, plus write down the second, diff the first. So in fact, on the left-hand side now, I have the derivative of x to the power of 4 times y. X to the power of 4 times y. Hang on. X to the power of 4 was the integrating factor. We should always end up with the integrating factor times y. Okay, well if that's the case, now I know what I can do. I'll integrate both sides. So x to the power of 4 times y must be the integral of 3x to the power of 6. Integrate that. 3/7 x to the power of 7 plus a constant. Well, that is an answer. If you want y as the subject, then we divide it. And here's the difference. Notice my constant now actually has a function of x attached to it. We won't necessarily have plus a constant by itself anymore. I mean, we could have other things. All right, let's do this one. Verify that this is actually a first order linear differential equation. It doesn't look like it at the moment because it's not in that format that we said. Because on the right hand side we don't have a function of x, we've got a function of x and y. Well, I could rewrite that right hand side. It's y on x plus 1. I could then move the y on x to the left hand side and it's now in the format of a first order linear differential equation. y dx coefficient's 1. Coefficient of y is some function of x, and on the right hand side we have some function of x. Oh, okay, it's a constant number, but it's still a function of x. So that's fine. Go work out our general solution then. Okay, work out my integrating factor. I want to integrate the coefficient of y, which is minus 1 on x. We get minus log x, so my integrating factor will be e to the power of that, which is 1 on x. I will multiply everything by 1 on x. That now means my left-hand side is the derivative of y on x. We should end up with the integration factor times y. Y on x will be the log of the absolute value of x plus a constant. Multiply both sides by x to make y the subject if we prefer. And there it is. X log absolute value of x plus some constant times x. Derivative plus 3y is equal to x. So yes, that is a first order linear differential equation. Integration, let's see. Integral of 3 dx is 3x. So this time my integrating factor will be e to the power of 3x. So I'll multiply everything by e to the power of 3x. Left hand side now becomes the derivative of y times e to the 3x. Integrate both sides. Now of course, we would never see one like this in extension 1. And this is an extension 1 topic because in order to integrate this, I would have to use integration by parts, which of course is part of the extension 2 course. But, you know, it's still good for an example to look at. I'll make u equal to x, du is dx, my dv will be e to the power of 3x, v is a third e to the 3x, so I have a third x e to the 3x minus a third the integral of e to the 3x. So integrate that. Divide everything by e to the 3x and I get y equals x on 3 minus a ninth plus some constant times e to the power of minus 3x. Okay, welcome to differential equations.